Hey everyone, it's Ms. Bell here from the Science Lab, and today we're going to be talking about a type of energy. There are different types of energy, but let me give you some clues so that you can take a guess on what kind of energy we might be talking about. I use this a lot at home when I make crafts and here in the Science Lab a lot. Also, clothes dryer. Think about an energy that might come from one of these items. What about a hot cup of tea or hot cocoa? What do you think? Or maybe an iron when you want your clothes straightened out? Or a big volcano and all the magma and ash and explosion coming out? What do you think all of these have in common? What about when you take your hands and you rub them together like this? What's created? What do you feel when you do that? You guys try it. Here's another big clue. Dun, da, da, dun. What do we get from the sun? Well, we get light energy for sure, but what else do we get from the sun? Or from fire or matches or candles? If I get close, what can I feel? I don't want to get too close. I don't want to burn myself, but the type of energy we're going to be talking about today is heat energy, or sometimes called thermal energy. We know that heat energy is a type of energy that we can feel with our hands and measure with a thermometer. All that heat energy from the sun can warm us up, and heat energy can melt things, and it can help us cook food by getting really hot temperatures underneath or around our food items. And there's all sorts of objects that produce heat, such as a light bulb, a toaster, fire, a blow dryer, and of course, our sun. Here are 4 objects that you might see in your home or even here in the Science Lab. We have a hair dryer, a lamp, a toaster, and a stove or a little burner top or hot plate. And with all 4 of these objects, they all have to get plugged into the wall outlet, and electricity comes through their cords, and that energy is then transformed into heat energy. But I want to take my thermometer and just see what the beginning temperature is before these are ever turned on, and then see what the ending temperature is after I turn them on and they start to heat up. I will need to be safe, so I'm not going to touch my burner or stick my hands in the toaster or touch the light bulb because I don't want to burn myself. So when I'm measuring my heated items, I'm just going to get my thermometer a little bit close without touching the thermometer or without touching my hand. So here we go. The hair dryer, that reads about 77 degrees Fahrenheit. And then my lamp or my light bulb, that is the same because they're all at room temperature, so that is about 76 degrees Fahrenheit. My toaster right here, That's about 76 as well. And, oh, can you make a prediction? Have they all been pretty much the same? Let's see. That is 76 as well. So now, let me turn all of these on. It might get a little loud because of my blow dryer. And let's give it, let's say a couple of minutes to heat up, and then I'll measure the temperature of all 4 of my objects. Here we go. Okay, so I'm going to start with my blow dryer. I've just turned it off, and I'm going to put it close. And I want to see what that temperature is. As you can see, my thermometer was not touching the blow dryer, but it was very, very close. And we were able to see that it got up to about, I think it was around 104 degrees Fahrenheit. And that's a huge difference from when we first measured the temperature before I ever turned it on. So I think it was around 76, and now it was about 104 degrees. And as this blow dryer remains off, that heat is going to eventually decrease, and it's going to start cooling off because the heat is going to be taken away or removed and no longer present in the blow dryer. Let's look at our toaster real quick. It's very warm to the touch. So before it was about 76 degrees, I believe. So now let's take a look, without getting too close, on how that temperature has changed since turning on the toaster. Again, I'm not going to get too close. So my thermometer went all the way up to 120 degrees Fahrenheit, which means it probably would have kept rising had I kept there any longer. But my thermometer just doesn't go that high. So as you can see, our toaster got super, super hot because of that heat energy coming from it. Okay, let's take a look at our lamp and see what temperature that light bulb got close to. So as you can see, our lamp got to about 94 degrees Fahrenheit. And the thermometer increased, the heat energy increased very slowly, not as fast as the blow dryer or the toaster so far, but we were able to see that increase for sure. Okay, let's go ahead and turn off our stove right here, and let's see what that temperature looks like when I place my thermometer close. that temperature is increasing very, very quickly, and that lets you know that this stove is still super, super hot. Just like our toaster, it kept going and going and going to where it'd probably get higher than 120 degrees Fahrenheit, but I don't have a thermometer that measures that high. So you have to be very careful with these appliances when you're working with them, either at home or at school, because you don't want to get hurt, you don't want to get burned, and this just shows you how extremely hot these items can get because of their heat energy. So not only will an object feel warmer if you get your hand close or maybe even touch that object, but sometimes that object gets so hot that it could even cause a burn and really hurt your skin. Another smart idea when dealing with heat energy is to have an adult be the one to handle those hot items. More than likely, you're going to need to use some sort of protective safety gear when handling hot items, such as an oven mitt or a pot holder, or maybe even a rag or a towel. Just something that you can put between your exposed skin and that hot item. When you heat materials, it actually causes that thermal energy to move throughout all the molecules within that object, and those move fast and further apart. And a hotter object is going to transfer heat energy to a colder object if those two objects touch and come in contact with each other. And that's why ice melts if you leave it out on a counter or if it falls, on the stove or something. The physical properties of some objects only change a little when just a little bit of heat is taken away. Take, for instance, this candle. When we added heat, it went from a solid to a liquid. And then when we took the heat away, that liquid wax turned into a solid. Here you can see my number 4 candle. The flame has already ran out because the wick just wouldn't continue burning anymore, but you can see all that reshaped wax. So the fire lit up the wax, it melted it, it ran down the candle, and then it started to kind of build up on top of each other down here. And because the fire ran out and it got away from the heat, it started to turn back into a solid. But over here, my fire's still going. You can see the top of my candle is in its liquid state. That wax is liquid, but the bottom is still solid because it's waiting to be melted after a long period of time. So we know when you add heat to an object, sometimes that heat might change the outer physical appearance of that object, or as we call them, physical properties. So with this experiment, I'm going to take a bar of soap like you see on the screen, and we're going to do a little fun experiment with heat. Now before we do that, I need to observe with my senses some physical properties of this soap. Just by looking at it, we can see that the color is a light green, and the state of matter, well, it's a solid. And when I hold it in my hands and put it up against the back of my skin, it has a cool feel to it. It's not warm, it's not room temp, it feels cool. And the shape, well, it's kind of an odd shape. If I run my fingers along the outlines of this bar of soap, it's kind of like a rectangle, but it's kind of curved on those two sides. So it's almost like an hourglass shape. So for the shape, I would say an hourglass rectangle. And as far as size goes, well, I would say if I had to compare it to two things, maybe like a marble and a book, I would say it's kind of medium in size, but I can be more exact and grab a ruler and measure the longest length of my bar of soap. And when I do that, it came out to be 9.5 centimeters. Now, touching the bar of soap, I'm trying to feel the texture, and it feels smooth and kind of waxy, like it leaves a residue on my fingertips. And as far as overall appearance, it has a glossiness to it, and on the top there's a imprint of Zest, which is just the company name of the soap. And the soap that I used in the lab actually was kind of chipped on one side. And the smell, oh, this bar of soap smells really good. And it just smells clean. It just smells clean. And as far as flexibility goes, well, it's very stiff. If I take it in my hands and I try to bend it, yeah, that's not happening. There's no flexibility to this bar of soap. Now that we've taken a look at the physical properties of our bar of soap, I want you guys to make a prediction about what will change, if anything, with the regular bar of soap after we heat it up. So we looked at its color, its shape, its size, the smell, the texture, and now I want you to think, how is this bar of soap going to change when we add heat to it, when we heat it up? Will it change at all? Will the color look different? Will the size look different? Think about it and make some predictions. So here I'm just going to put my chunk of soap into a microwave, and that is going to act as our heat source. And we're going to see what the soap will look like after heat is added to the soap. Okay, here is our soap after it has been microwaved. It deflated a little bit from when I first took it out of the microwave, but for the most part, this is what it looks like. I'm going to try to transfer it back onto our plate so that we can get a better look at how it appears. As far as the color goes, it you can see some of the light green pieces over here, but it kind of turned into like a tannish, like a really, really creamy light brown. And the state of matter, well, it's still a solid. There are hard pieces like the original soap pieces, and then there's some softer sides over here, but it's still a solid. The relative temperature, well, it is definitely warm. I'm still able to place my finger on it and not move it away real quick. So it's not extremely hot, but it's warm to the touch. And its shape, well, it doesn't really have a shape anymore. It's just like a puffy blob. And its relative size, well, that little chunk that we cut off was maybe about this size, so right here, that rectangular size. So it's bigger or larger than that small chunk that we cut off. But if we take a ruler and we hold it to it, we can see going this way, it's stops right here, so 6 centimeters, or if we go this way, it stops at 7 centimeters. So I'm going to say 7 centimeters with its length. And with its texture, well, it's like spongy, very squishy. And its appearance, well, it looks puffed up. It looks kind of cracked in some places, so it also looks bubbly and almost like cake, or like a cupcake, like the little crumbs that you might see when munching on a cupcake. And its smell, well, to be honest, it kind of smells burnt. When I microwaved it in the microwave, I think I did it for about 45 seconds, and there was some smoke coming out of the microwave, so it smelled a little burnt. And as far as flexibility goes, it's at first it was very spongy, and I was able to bend it without it breaking, but as you can see, as I'm starting to bend it ever so slightly, like pieces are starting to crumble off and break off. And that's only because it's sitting here and heat is slowly escaping from it. So when it first came out of the microwave, I would say it was only somewhat flexible. So we just finished looking at all of the physical properties of our bar of soap after we added heat, and now it's time to wait. And what are we waiting on? Well, we gotta wait for it to cool off, and who knows how long that's gonna take. Is it gonna be, what do you think? Think about it. We heated it up in the microwave, it got really warm, and it needs to completely cool off. How long is that gonna take? 5 minutes? 5 hours? 30 minutes? Or a couple of hours? Well, only I will be able to figure that out here in the science lab, but when it does cool off, we're going to look at it again, check out those physical properties again, and see if anything changed. Okay, so here is our soap. It has been about an hour and a half after I heated it up, so now it's all cooled off. And I'm going to talk you through the physical properties with this soap. So the color did not really change after it heated up. So it still has this creamy light tan color mixed with some of the original light green soap pieces. And as far as state of matter, well, it is a solid, and it's a hard solid again, so it's not soft anymore. It went back to being a hard solid. And relative temperature, well, It's not cool. It's definitely not warm. I would say this is kind of neutral. I would say it's room temperature. And as far as its shape goes, well, there's really no real shape to it. It's all broken into small pieces and chunks. And its size, well, let me grab my ruler. This shows that it's about 7 centimeters this way and about, I would say 6 centimeters this way. So the length this way didn't change after I heated it up, but you know what? When I first took it out of the microwave, it was like poofy. It had like expanded. But as it has cooled off, it's kind of shrunk in size. So I would say it was somewhat smaller than the soap after it was heated up. And its texture, well, it's really rough. It's not smooth, and that's because it's so crumbly. And its appearance, well, it's broken, of course. You can see all the pieces into all these chunks, and it's still cracked looking. So it looks like a really, really dry, old cake versus that newly baked cake before. And smell, okay, give me a second. Ooh. Oh, I was not expecting that. You know what? It actually smells like its original good smelly soap again. It doesn't smell burnt anymore. And for flexibility, well, let's see. It is not flexible. As you can see, I just broke off a piece. I wasn't even really trying that hard. It is hard. You can hear and these little crumbs are like falling off everywhere. But it is not, oop, there goes another piece. It is not flexible at all. If I try to bend this or reshape it, it's going to break off, as you can, as you can see right there. So after you're done with heating your bar of soap and then letting it cool off, you're able to look at all of this data that has been filled into this chart. And you can see what's the difference in all of these physical properties before we added heat, after we added heat, and after we removed that heat. So did the soap look different after it melted? And then did it look even more different after it cooled off? This is when you're able to look at all the different information and then compare and contrast and see what's similar and what's different.